If you turn this video to one point off, then please tell me what the reason was so that I can improve. Otherwise, hi and welcome. I'm trying to learn particle physics today, how the Higgs was found, and after we've done that, we're gonna do standing yoga. And if you participate in the standing yoga, then it's at your own risk. And this is part 2 or 3 of this, how the Higgs was found. In 1964, theorists Robert Rode and Francois Englert devised the equations of the quantum field that would pervade the cosmos and break electroweak symmetry by being consistent with relativity. Physicist Peter Higgs made the same proposal and pointed out that ripples in this field would take the form of a new particle. Later that same year, Gerard Gornik, Carl Hagen and Tom Kibble combined these ideas into a more realistic theory that was a precursor to the standard model. Now it was about the process by which the electroweak force splits into the electromagnetic, and the weak force is known as electroweak symmetry breaking, and must have happened sometime in the universe's early moments. So the electroweak force was split up into the electromagnetism and the other one. One weak force, the nuclear weak force, probably, the weak nuclear force. And whatever caused it is clearly connected to the mystery of mass. After all, it is the mechanism by which the W and Z bosons acquire mass. So the breaking up of electroweak force into electromagnetism, electromagnetic and weak force. The central point about what came to be known as the Higgs field is that even in the lowest energy state of space isn't empty. Particles traveling through space interact with the field to different degrees, and this creates a sticky quality to the movements, mass. So there is a field which is everywhere, it is not enough, it is not empty, and by having a stickiness to this, then we're moving along this, or by having a stickiness because of that thing which is there, even though there is technically, there is something, but it's not empty. And that creates a mass. The W and Z boson acquire their mass by one kind of interaction with this field, but fermions do so by another. Because the Higgs field has no net electric or color charge, photons and gluons don't interact with it at all, and so remain massless. So the Higgs field seems to be the thing which gives all the other particles a stickiness, because that thing is not empty, and so we're having mass, but not the gluons and photons, because the Higgs field itself does not have electric or color charge, and therefore photons and gluons are not stick to it, and they don't have now mass, and they are massless. This was a neat trick. To find out if it was anything more, we needed to expose the field by making it wobble. Those wobbles being observed as Higgs bosons. Theoretical and experimental developments gave us a good idea of the energy required. The Higgs boson's mass had to be between about 100 and 400 giga-electronvolts. We would need a truly huge machine. The Large Hadron Collider at CERN near Genua in Switzerland is housed in a 27-kilometer long tunnel. It is commonly described as a ring, but is actually more like an octagon with rounded corners. In the straight sections, intense electromagnetic fields kick two counter-circling beams of protons every time they come past, increasing their speed. By the time of collision, they have reached 99.99991% of the speed of light. So, to find out if it was anything more, we needed to expose the field by making it wobble, those wobbles being observed as Higgs bosons. Theoretical and experimental developments gave us a good idea of the energy required. Okay, let's see it on. Bending such a fast-moving beam of particles requires very powerful magnets. Any power lost to electrical resistance would be a brake on performance, and so the magnets are made of supercooled superconducting materials. Even then, they can only achieve gentle curving, hence the LGH's vast size. On 4 of the octagon sides, so an octagon has not 4, but 8. 8 borders. It has 2, 2, 2, and 2. 2, 2, 2, and 2. On 4 of the octagon sides, more magnets constrain the proton beams to a fraction of the thickness of a human hair and bring them into a head-on collision. 4 large detectors record their results, one at each point, at ATLAS, CMS, LHCb, and ALICE. ATLAS or ATLAS and CMS are all-purpose detectors designed to measure whatever pops up, including the fleeting trace of Higgs boson. When 2 protons collide at the heart of the LHCA's ATLAS or CMS detectors, they split into their constituent quarks and gluons, which decay further into myriad particles spreading out in all directions. Okay, when these 2 protons now hit, they're breaking up into the quarks and gluons. The quarks are inside of them and making up the proton, and the gluons are transmitting the force between the quarks, holding them together and making therefore the proton existable. I think. But it was something like that from the principle. Each detector is made up of concentric cylinders. Those closest to the collision point are made of a semiconductor. If an electrically charged particle passes through the semiconductor, it liberates the material's loosely bound atomic electrons, creating a pattern of electrical currents that allows a precise measurement of the particle's path. So we're having a semiconductor down there. In the semiconductor, the thing is, it can be easily a plus thing or a negative. It can be easily positive or negative, because it was about a photon. I once made a long video about it. It had 4 or 5, and so it could easily go to 6 or 4 electrons or something like that. It can very easily gain an electron and lose one. And whether it gains or loses one makes it positive or negative. That is the important thing in computers. You can have a little semiconductor cell in a computer. You can easily just with 1 electron make it positive or negative. In other words, you can say if it's positive, it is a 1. If it's negative, it is a 0. And you can make that very easily, millions of them in just a split second, turning them positive or negative just with adding 1 electron. In other words, just leading a little bit of current into it, making it a positive. It is now 1, 0, 1, 0, 1, 0, 0. And this combination of 1s and 0s make them the letters into the calculating thing for a computer. What we're here doing is whatever particle smashes into it, I don't know if it's catching it or whatever, that little thing has a little influence on it, on the semiconductor, and that little particle has a little negative charge and makes them there also at some points a little negative charge, very small, very little, very precise, and we don't know exactly where it was that thing. It's not like that. I don't know if it's actually a catch thing and it swipes over it or something. It would be really cool. Magnets surrounding the detector cause the paths of a charged particle to curve, with a degree of curvature representing the particle's momentum. So there are magnets, and they are pulling at that little particle, and with that way we also know more about the curve. How heavy it is, I don't know. The next cylinder outwards consists of detectors filled with liquid argon, or lead tungstate crystals. Collisions with the densely packed atoms in these detectors stop most particles in their track, and photons emitted as the particles decelerate can be used to measure the particles' energy and so identify them. Okay, there we go. Collisions with the densely packed atoms in these detectors. In the photons emitted as the particles decelerate. Okay. We're having there this dense argon and this dense other tungstate crystals, so very dense crystals. And now the particle bangs into it and it's stopped, like a car comes into the stop point for the experiment. And when it thing stops, it breaks down again into photons. And these photons can be measured, what it is. Now we know how much energy the particle had. Now we can calculate what particle was it, because particles have different forms of energy. The heavier variants of electrons, known as muons, aren't stopped by these detectors, but are identified and measured by the next cylinder of dedicated detectors. The even more reclusive neutrinos aren't measured at all. Their presence is instead deduced by totting up the monuments of all the other particles produced in a collision and seeing if anything is left unaccounted for. They're having neutrino detectors at other places. I also did a video once about it. I don't really understand it. We're having these things and we are measuring now what was a neutrino. They know what a neutrino is, and so they don't have to measure it at the LHCb at the Large Hadron Collider. They just subtract it. A Higgs boson is short-lived, decaying almost instantaneously into other particles. To infer its presence, we must measure these decay products and look for evidence that they come from Higgs. Okay, they found only the rest products of the Higgs. Fortunately, the standard model predicts everything we need to know about the Higgs boson, apart from its precise mass. For every possible mass, we can predict the number of Higgs particles that the LHCb should produce and what they will decay into. For example, the Higgs should sometimes decay into pairs of high-energy photons. Because momentum is conserved in particle decay, the momentum of the photons can be translated into the mass of the particle that produced them. They can measure the photons. That was the thing before. The photons and how much, or whatever the photons were, they know how much energy it has. And it is possible to calculate energy and how much Higgs was there. The momentum of the photons can be translated into the mass of the particle that produced them. Because E equals mc squared? Maybe, I don't know. There are many possible sources of a photon pair. But if we concentrate on the likely looking ones and plot their combined momentum on a histogram, an unknown particle will make itself known as a bump, an excess of events corresponding to a particular mass. This is what both Atlas and CMS saw at a mass of around 125 giga-electronvolts, which was announced to the world on 4th July 2012 as the Higgs boson. So they found the bosons, measured them and said there's only one source for it, that is the Higgs boson. There was a Higgs boson a second ago. We found now the photons, there was a Higgs boson, and we found whatever, 4,000 bosons. Ergo, I think it would make sense. I have no idea, but it would make sense. At least it is something so we can follow and understood. We can get them the right formula. The energy equals mass times, what's even C? Time, space, whatever, squared. So we can calculate. We found so much photons with that energy. It was a Higgs 125 giga-electronvolts. It wasn't the only evidence. The Higgs boson is also expected to decay into two Z bosons, which each decay further to 2 leptons. Combining the momentum of these leptons produced peak at the same mass visible in the photon data. Combining the mass of 2 leptons gave the same mass as was there. And that means that the Higgs is decaying into 2 Z bosons. W bosons added their own strand of evidence. These particles decayed into neutrinos, which aren't detected, so there's no definite mass bump in this case. Instead, we just see more W decays than we would expect if the Higgs didn't exist. All in all, the evidence was just enough to grab a gold standard 5 sigma discovery, signifying a probability of just around 1 to 3.5 million, but the finding came about as a result of random statistical noise. They fastened up protons in the thing, let them bump together. When they bump together, all the particles coming out of them, the quarks are measured by some things, the other ones are some things. The photons coming against semiconductors, the photons having a little, they are charges, whatever. They are making a little movement to these charges and swapping the switches off. It doesn't really matter, maybe it's something else I'm explaining. Now you see there was a photon, there were 4 photons, ergo there was a Higgs, because we know all the other particles, it must be the one we're missing. If we find 2 Z bosons, it makes the Higgs boson, so we know W bosons come from the neutrinos. They could be measured somewhere else. There were more W found somehow. And now we know the Higgs was there. Because there was so much photons which came from nothing else. All the other particles were filtered out by the other things. By the first station. The first one figured out the one, and only the Higgs went through. Maybe it was bad. Whatever. They found them there, the evidence of that, the disposal products of it, the photons, and could calculate back the Higgs was there. That was the particle physics part. If you were here for particle physics, you can go directly to the next part of particle physics. If you stay here and participate in the 10 seconds you're going to brief into the answer. Out and down. Up. Out and down. Breathe into the arms up. Bring the hands to touch and lower hands down to answer. No, we don't have time left. I thank you very much. And until next time.